Okay, for question 1, it's talking about the atmospheric pressure on Mars, which is 0.007 atmospheres. On Earth, it's 1 atmosphere, and so the pressure on Mars is much, much less. What the air pressure does is the air pressure presses down on the liquid, and of course the air pressure is pressing in all directions, but one of those directions is the downward. And so since the air pressure is pressing down on the liquid, the person's mouth attaches to the straw and sucks the air out of the straw, creating a low pressure environment. So the low pressure here compared to the higher pressure outside causes the liquid to be pressed through, into and through the straw. Now, the lower the pressure outside the straw, the lower the pressure inside has to be, because the pressure inside the straw must be lower than the atmospheric pressure. With such a low atmospheric pressure on Mars, it's going to be very difficult to create such a low pressure environment inside that straw. So it will be harder to drink out of the straw on Mars. Okay, with question 2, I think it was clear enough. The answers in the back of the book were good enough. But for question 12, B, it says that the water and carbon tetrachloride do not mix as liquids, but their vapors mix really well. Homogeneous means that they mix perfectly. The reason for that is liquids are so close together that for liquid molecules to mix, the intermolecular forces between them must be similar. So polar liquids will mix with other polar liquids. Nonpolar liquids will mix with nonpolar liquids. Carbon tetrachloride is nonpolar, whereas water is polar. In the gas, the molecules are far apart. Their intermolecular attractions, therefore, the attraction between molecules, don't really matter so much. So if this is a polar molecule and this one is nonpolar, they can still intersperse just fine, because in gases being so far spread out, their intermolecular attractions are really not a big factor in their properties. So because intermolecular forces don't matter as much, polarity doesn't matter as much, and the two gases can just fill the same container and disperse with no problems. Okay, with 19A, you simply take the given pressure of 265 torr and divide by 760 torr per atmosphere, and that gives you 0.349 atmospheres. For B, we take our 265 torr and realize a torr is the same thing as a millimeter of mercury, so our answer is just 265 millimeters of mercury. For C, it's probably the most complex one. You want to first convert to atmospheres. Take 265 torr, divide by 760 torr per atmosphere, and then multiply by 101.325 kilopascals per atmosphere, and we get an answer of 35,300 kilopascals. Now 23, the open and closed end manometers. We want to start with, first of all, changing the atmospheric pressure of 0.985 atmospheres, changing that to millimeters of mercury by multiplying 0.985 times 760 millimeters of mercury per atmosphere. We will get 748.6 millimeters of mercury. That is the pressure outside the manometers. Okay, when dealing with manometers, you're dealing with millimeters of mercury, or in this case, centimeters of mercury. Just realize that 52 centimeters is the same as 520 millimeters of mercury. So, there is, just according to our previous conversion, 748.6 millimeters of mercury is pressing down right here. The gas inside the chamber is pressing on the other end, and it's pressing this way. There is a height difference. You can tell from the drawing that the air outside is pressing down harder than the gas inside the closed, or the inside the manometer here. What is the difference? The difference is a height of 52 centimeters or 520 millimeters of mercury. So the outside pressure is 520 millimeters greater than the gas. So to figure out the gaseous pressure, simply take the outside 748.6 millimeters and subtract 520 millimeters. Our final answer will be 228.6 millimeters of mercury. And don't write in your textbook the way I am. All right, the second one, again, it's an open-ended manometer. The outside pressure is the same. There is a pressure pressing down of 748.6 millimeters of mercury. This time, however, we can see that the gas that's pressing on the inside is pressing harder. It's pressing down harder than the atmosphere. And so the height difference of 67 millimeters is caused, it's because the gas pressure is 67 millimeters greater than the outside pressure. And so we simply take our 748.6, add 67, and we get 815.6 millimeters of mercury for our pressure. Now, when the manometer is closed here, it's not open to the atmosphere, so technically the atmospheric pressure doesn't matter at all. How hard the gas is pressing, it's the difference in height of 10.3 centimeters. And so that height is 103 millimeters of mercury. Okay, the difference in height is the gas pressure. Now, if you need to convert each of these pressures to atmospheres, you simply take the numbers we got, which were in millimeters per mercury, and divide by 760, because there are 760 millimeters of mercury for each atmosphere. All right, 26A, the answer is 2.31 liters, and it tells you to use Boyle's law, which is just P1V1 equals P2V2, and I think you guys are pretty good at that. With part B, it says use Charles' law. That's V1 over T1 equals V2 over T2, and the final answer you get should be 6.67 liters. And lastly, the stoichiometry problem, they give you a perfect stoichiometric ratio. The amount of hydrogen is 3.6. That is triple the amount of nitrogen, which works just fine. So there is no limiting reactant. They're both just fine. So pick one of them. The amount of NH3 needs to be double the amount of N2. So 2.4 liters is your final answer. If you took 3.6, multiplied by 2, divided by 3, you get the same thing.